The most powerful aircraft carrier ever built is not sitting in a harbor. Right now, it is cutting through the open ocean, armed with weapons and technology never before seen on any warship in history. The Gerald R. Ford-class aircraft carrier has been loaded with systems so advanced they make many other warships around the world look outdated. And today, we are going to break down every one of those powerful systems, step by step. Introduction. The Gerald R. Ford-class aircraft carrier is not simply a larger version of previous aircraft carriers. It was built as an entirely new war machine from the ground up, designed with next-generation technology, advanced weapons, and a completely different approach to naval warfare. Nearly every major system on the ship was redesigned. The aircraft launch system, the landing system, the radar systems, the weapons, the power generation network. Everything was rebuilt to be faster, stronger, and more capable than anything that came before it. And this matters now more than ever. Around the world, military tensions are increasing. China has launched its most advanced carrier program yet, while threats against U.S. naval forces continue to grow across key regions. The United States Navy did not answer those threats with small upgrades or temporary fixes. Instead, it responded by creating what many consider the most powerful strike platform ever deployed at sea. These carriers are already operating today, carrying weapons and systems unlike anything previously seen on a warship. Before we break down those weapons one by one, leave a comment below. Which system do you think is the most important for maintaining America's dominance at sea? Now let's begin with the first major system, one that completely changed the way the Navy launches aircraft forever. Emails, the launch weapon. For more than half a century, every carrier in the United States Navy launched aircraft using the same basic method: steam catapults. A massive burst of compressed steam slammed into a piston system, launching aircraft down the flight deck and into the sky. The system worked. It had been reliable since the era of World War II, but it also had major drawbacks. It was violent, extremely heavy, required huge amounts of fresh water, and struggled with certain aircraft types. The Gerald R. Ford-class aircraft carrier replaced that entire system with the electromagnetic aircraft launch system, better known as emails. Instead of using steam pressure, emails relies on powerful electromagnetic energy to accelerate aircraft along the deck. The result is a launch that is smoother, more controlled, and far more precise. Unlike older catapults, the system can adjust its power output depending on the aircraft being launched. From a heavily loaded Boeing FA-18E and F-18 Super Hornet to a lightweight reconnaissance drone. And that difference is critical. Traditional steam catapults delivered force too aggressively for many lighter unmanned aircraft, creating stress that could damage or even destroy them during launch. Emails solved that problem completely. For the first time, U.S. carriers can efficiently launch an entirely new generation of unmanned aircraft capable of reconnaissance, strike missions, electronic warfare, and support operations alongside manned fighters. The performance numbers are equally impressive. The USS Gerald R. Ford was designed to generate around 160 aircraft sorties per day during standard operations. During full combat surge conditions with non-stop flight activity, that number can increase to as many as 270 sorties within a single 24-hour period. No aircraft carrier anywhere in the world has ever achieved operational numbers at that level. Emails alone made the Ford-class carriers revolutionary, but launching aircraft is only half the battle. Eventually, every aircraft has to return safely to the ship, and that is where the next major system becomes just as important. AAG, the recovery weapon. Landing a fully armed fighter jet on the deck of a moving aircraft carrier is one of the most dangerous tasks in military aviation. The aircraft approaches at high speed, slams onto the flight deck, and catches a steel arresting wire with its tail hook, bringing the jet to a complete stop within just a few hundred feet. For decades, the system controlling those arresting wires relied on hydraulic technology dating back to World War II. It worked, but it had limitations. The old hydraulic systems applied nearly the same stopping force to every aircraft, whether it was a heavy fighter loaded with fuel and weapons or a much lighter aircraft. There was very little flexibility. The Gerald R. Ford class aircraft carrier changed that completely with the advanced arresting gear known as AAG. Instead of traditional hydraulic systems alone, AAG uses advanced energy-absorbing technology combined with water turbines that automatically adjust resistance based on the exact aircraft landing on the deck. If a heavily loaded fighter arrives at high weight, the system increases stopping force. If a lighter aircraft or unmanned drone lands, the system reduces resistance automatically. Every landing receives precisely the amount of force required, nothing more and nothing less. That makes aircraft recovery significantly safer for pilots. It also reduces long-term stress on landing gear, airframes, and carrier aircraft structures, helping extend the service life of the Navy's aviation fleet. More importantly, AAG allows the carrier to safely recover a much wider range of aircraft types, including lightweight unmanned systems that older hydraulic arresting equipment would have struggled to handle safely. And this is where the bigger picture becomes clear. The combination of emails and AAG created the world's first fully electromagnetic aircraft launch and recovery environment aboard a carrier. These systems were not built only for today's aircraft. They were designed specifically with the future of unmanned naval aviation in mind. Drones and autonomous aircraft that are becoming more advanced and more operational with every passing year. Together, emails and AAG completely changed how carrier aviation works, and they also prepared the ship for the next generation of weapons already entering service. Systems that are proving themselves in real-world operations and forcing adversaries to rethink how they challenge a U.S. carrier strike group. F-35C, the stealth strike weapon. The Lockheed Martin F-35C Lightning II is the Navy's carrier-based stealth fighter, but calling it simply a fighter jet does not fully explain what it really is. The F-35C is a flying combat network. It carries weapons, gathers intelligence, shares targeting information across an entire strike group, and coordinates attacks in real time. Unlike older fighters, the F-35C stores its weapons inside sealed internal weapon bays, rather than hanging them under the wings. That design dramatically reduces radar reflections caused by external missiles and fuel tanks. To enemy radar systems, the aircraft presents an extremely small signature, making it one of the hardest combat aircraft in the world to detect at operational ranges. Its unrefueled combat radius is roughly 1,200 nautical miles, meaning it can travel long distances, engage targets, and return without needing fuel support. With aerial refueling, its operational reach extends even farther, allowing carrier-based strikes against targets deep inside hostile territory. But the F-35C's greatest strength is not what it can do alone. It is what it allows the entire carrier strike group to accomplish together. Using its advanced sensor suite, the F-35C can penetrate heavily defended airspace, locate enemy targets, identify threats, and transmit targeting data instantly through secure battlefield networks. That information can then be shared directly with Boeing F/A-18E/F Super Hornet aircraft operating farther away from enemy defenses. The Super Hornets can launch long-range missiles from safer positions outside hostile engagement zones, while the F-35C remains difficult to detect. In many scenarios, the F-35C finds the target, tracks the target, shares the targeting data, and disappears before the enemy even realizes it was there. The strike aircraft behind it deliver the actual attack. This type of networked warfare, where one aircraft acts as the eyes and another delivers the firepower, has become one of the most powerful advantages of modern U.S. naval aviation, and every Gerald R. Ford-class aircraft carrier operating the F-35C is built around that capability. But the long-range missiles carried by those Super Hornets introduce another level of power entirely, one that many people still know very little about. Al-Racem, the thinking missile. Most anti-ship missiles fly in a straight line. They are fast and powerful, but once launched, they simply go where they are aimed. The AGM-158C long-range anti-ship missile, better known as LRASM, works very differently. This missile is equipped with an advanced artificial intelligence guidance system that allows it to react and adapt during flight. Instead of following a predictable path, LRASM can navigate around threats it detects along the way. It flies extremely low over the ocean's surface, almost at sea level, helping it stay underneath enemy radar coverage for as long as possible. As the missile approaches its target, it scans the enemy warship and identifies the most vulnerable area to strike. It does not simply aim for the center of the ship. It selects critical sections designed to cause the maximum possible damage. Its exact range remains classified, but publicly available information confirms that LRASM can strike targets at far greater distances than many previous anti-ship missiles. The missile was specifically designed to defeat some of the most advanced naval air defense systems in the world, systems created for the sole purpose of intercepting incoming missiles like this one. In October 2025, the AGM-158C long-range anti-ship missile was also integrated onto the Boeing P-8 Poseidon maritime patrol aircraft, giving the Navy another launch platform beyond carrier-based fighters. That means the Navy now has multiple independent ways to deploy the same weapon, from fighters operating off the carrier to long-range patrol aircraft flying far from the strike group. When combined with the advanced targeting capabilities of the Lockheed Martin F-35C Lightning II, LRASM creates a kill chain that is extremely difficult to stop. The F-35C can detect and track enemy targets deep inside defended airspace while remaining difficult to detect itself. It can then share targeting data with aircraft carrying LRASM missiles outside enemy defensive range. In many cases, the target may not even realize it is being tracked until the missile is already approaching inside its defensive perimeter. That creates a major tactical advantage for every Gerald R. Ford-class aircraft carrier strike group during deployment. But offensive power is only one side of the equation. Survivability matters just as much, and the defensive systems aboard the Ford-class carriers are every bit as advanced as their strike weapons. Dual-band radar and the defensive shield. The Gerald R. Ford-class aircraft carrier was not built only to strike targets with overwhelming force. It was also designed to see and track nearly everything happening around it. At the center of that capability is the dual-band radar system, often called DBR. This system combines two separate radar technologies into one fully integrated platform. The S-band radar handles long-range wide-area surveillance, scanning enormous sections of airspace to detect incoming aircraft, missiles, and potential threats far from the carrier group. The X-band radar focuses on precision tracking, locking onto identified targets with far greater accuracy once a threat has been detected. Working together, these radar systems can detect, track, and manage hundreds of airborne threats simultaneously at ranges older radar systems could never achieve on their own. Because both radar systems are integrated into a single compact array, the carrier's island superstructure is smaller than the one used on older Nimitz-class aircraft carrier vessels. That smaller island reduces the ship's radar cross-section, making the carrier itself more difficult to detect at long distances. Every part of the ship's design was planned with purpose. The dual-band radar system feeds directly into the carrier's integrated self-defense network, combining information from multiple onboard sensors into one unified tactical picture for the crew. That means commanders receive a constantly updated view of every threat in the battle space, with fewer blind spots and faster reaction times. For threats that break through the outer defensive layers, the carrier carries additional protection systems. These include fast-reacting surface-to-air missile systems designed to intercept incoming aircraft and anti-ship missiles before they can reach the ship. Behind those defensive layers sits the Phalanx Close-In Weapon System, commonly known as CIWS. This radar-guided rotary cannon fires up to 4,500 rounds per minute at incoming threats that penetrate the final defensive perimeter around the carrier. Together, these systems create a layered defensive shield that is redundant, fast-reacting, and extremely difficult to penetrate. But even these advanced weapons are only part of the future, because the next generation of carrier defense may not rely on ammunition at all, and the Ford-class carriers were designed from the beginning with enough electrical power to support those future weapons systems. The power behind future laser weapons, the USS Gerald R. Ford, is powered by two A-1B nuclear reactors. Together, those reactors generate more than 100 megawatts of electrical power, over 3 times the electrical capacity produced by older Nimitz-class aircraft carrier ships. The Nimitz-class generated around 4,160 volts of electrical power. The Gerald R. Ford generates approximately 13,800 volts. That enormous increase was not accidental. It was built into the ship from the very beginning for one major reason: the future of naval warfare. Next-generation directed energy weapons, including high-powered laser systems, require massive and sustained amounts of electricity to operate effectively. Older carriers simply were not designed to support those energy demands. The Ford-class carriers were. Senior United States Navy officials have already confirmed that directed energy weapons are being actively developed for future deployment aboard aircraft carriers, and the Ford class already has the infrastructure needed to support them. The ship has the electrical output. It has the available internal space, because removing the older steam-powered launch systems freed up large sections inside the carrier, and the carrier's internal architecture was designed from the start to allow future laser weapons to integrate directly into the ship's combat systems. Once operational laser weapons are deployed aboard these carriers, the economics of naval defense could change dramatically. Traditional missile interceptors are extremely expensive and limited in number. Laser weapons, by comparison, cost very little per engagement because they rely primarily on electrical power generated by the ship's reactors. As long as the carrier has power, the weapon effectively has an almost unlimited magazine. And unlike conventional missiles, a laser strikes its target at the speed of light. There is no travel time. No incoming missile, drone, or aircraft can outrun the beam itself. The Gerald R. Ford-class aircraft carrier was designed with that future already in mind. It does not require a complete redesign or massive retrofit to support these systems. The ship is already prepared for the next generation of naval warfare: unmanned aircraft and the growing fleet. The final piece of the Ford-class carrier system is unmanned aviation. The Boeing MQ-25 Stingray is the Navy's first carrier-based drone specifically designed to operate directly from an aircraft carrier flight deck. Its primary mission is aerial refueling, allowing carrier-based fighters to extend their combat range during long-distance operations. But the aircraft represents much more than a flying fuel tanker. As the technology continues to mature, the MQ-25 Stingray is also being considered as a future reconnaissance and strike platform for carrier operations. Initial operational testing for the Boeing MQ-25 Stingray was planned for the mid-2020s, with the Navy continuing to move toward full operational deployment. Once fully integrated into the fleet, the drone will significantly extend the operational reach of the Lockheed Martin F-35C Lightning II and the Boeing F/A-18E/F Super Hornet. It will also reduce the need for pilots to perform dangerous non-combat refueling missions, lowering operational risk during extended deployments. More importantly, it opens the door to an entirely new era of carrier-based unmanned aviation. And this is where the Ford-class design becomes especially important. Emails can launch the MQ-25 Stingray. AAG can recover it safely. The carrier's electrical and combat systems were designed to support it from the beginning. Every major system aboard the Gerald R. Ford-class aircraft carrier works together as part of one integrated combat platform. That is what truly separates the Ford class from previous carriers. It is not simply a collection of upgraded parts. It is a fully connected system designed to evolve alongside future technologies throughout its entire service life, and the fleet itself continues to grow. The USS John F. Kennedy, CVN-79, is expected to join the fleet in the coming years. The USS Enterprise, CVN-80, will follow after that, with additional Ford-class carriers already planned behind them. The Navy's long-term strategy calls for a full fleet of Ford-class carriers to gradually replace the older Nimitz-class ships one by one. Each of those future carriers will deploy with the advanced systems discussed here today. And every one of them is being built ready for the next generation of naval warfare, including autonomous aircraft, advanced networking systems, and future laser weapons, still moving toward operational deployment. Conclusion: China's newest aircraft carrier, the Fujian, was officially commissioned in a ceremony attended by Xi Jinping. It represents a major advancement for the Chinese Navy and introduces several modern technologies, including an electromagnetic aircraft launch system. But there are still major differences between the Fujian and the new Gerald R. Ford-class aircraft carrier operated by the United States Navy. The Fujian is not nuclear-powered, which limits the amount of electrical power it can continuously generate for future high-energy systems, such as advanced laser weapons. The United States Navy also holds decades of real-world operational experience built through carrier deployments across multiple regions around the globe. That experience matters. Carrier warfare is not only about technology, it is about coordination, logistics, combat operations, and the ability to sustain global naval power over long periods of time. And the United States continues to expand that advantage. The most advanced weapons ever deployed aboard an aircraft carrier are already operating today under the American flag. More Ford-class carriers are still under construction, and the technologies being developed right now, from autonomous aircraft to directed energy weapons, will make these ships even more capable in the years ahead. This is not a distant concept or a future proposal. It is already happening. If you want to stay updated on military technology, naval warfare, and the next generation of American military power, make sure to like the video and subscribe so you do not miss the next upload.